So yes, my talk today is based on a work I did during my master's at the University of Guelph with the machine learning research group, where I tried to model structure mapping as inductive bias in a neural network. So inductive biases are essentially a fancy term for operator design choices in neural network design and training. Before I start, I would like to start with the disclosure. My background is in mostly computer vision and machine learning. I'm nowhere near an expert on analogy or cognitive science in general. So if you have any clarifying questions, you may ask in the chat. I would be happy to answer them. If you would like to correct me at some point, I welcome that as well. So here is a brief outline of my presentation. I'll start with a brief motivation of the problems and current status of deep learning-based computer vision. And next, I'll talk about some background. So I'll talk about visual reasoning problems and the pros and cons of neural and symbolic AI when it comes to reasoning. Next, I'll discuss the neural structure mapping framework, which is the work I did. And this framework tries to explicitly utilize the relationship structure of a reasoning problem into the neural network layout as a prior. And I would say this is still a work in progress. So we published our initial results at a workshop in December, but we are still working on this. So I'll discuss some open questions in our work at the end of this section. And lastly, I'll briefly cover a parallel work I came across very recently. So this work is called Neural Interpreters, and it's from researchers at the Max Planck Institute and the Montreal Institute of Learning Algorithms. This was also presented at the same conference in December. But I found that the paper fleshes out some ideas and some open questions which were lingering in our work. I feel like this paper did a very good job at sort of addressing them. So I'll briefly present an overview of this work. And for clarification, this is not my work. This is work done by researchers at the Max Planck Institute and the Montreal Institute of Learning Algorithms. So I would like to reflect on the general state of problems and methods in computer vision that motivated this work. So at the low level in computer vision, there are problems related to pattern recognition. These used to be solved by heuristics in the past, such as like edge detection algorithms and stuff. But more recently, deep learning-based approaches that learn feature representations have been shown to perform better at generalizing to unseen data for these pattern recognition sort of tasks. However, these deep learning models tend to perform poorly on tasks where, like on tasks that require reasoning and planning, or when it comes to sort of explaining their decisions. And looking forward, there are challenges in higher order cognition, like generalizing to data from a new distribution, learning causal decisions, learning in an embodied setting where there's an agent which interacts with its environment to perform learning. These are still open challenges for deep learning-based computer vision. And while this sequence of challenges lies on a continuum, but in general, the problems like on the left, which I highlighted with green, have been addressed better than the problems on the right. And some of the failure modes of deep learning include shortcut learning. So deep learning tends to learn solutions which work as intended on the test set, but do not rely on the correct discerning feature under the hood. So an example that I show here is failure to recognize an object in the absence of a frequently co-occurring background. This was shown by Beery et al. That deep learning models tend to perform poorly when the co-occurrence statistics are changed in the test distribution. Next is out of distribution generalization. So deep learning models suffer from significant drop in performance because they overfit to the data distribution. So for example, models failing to recognize objects when the geographic location of the object is changed. This was shown by DeVry et al. Another concern is that deep learning models lack interpretability, and even the current methods for interpretability in deep learning are somewhat unreliable, non-specific, and often not falsifiable. So in this paper by Kindermans et al., they showed that saliency-based interpretability methods sometimes generate attribution pixels when which have nothing to do with the image class. So for example, overlaying a cat image on a digit leads to attribution pixels on the cat, which has clearly nothing to do with the digit class. And since deep learning models often rely on low-level features like image texture, object count, object co-occurrence, etc., they struggle with reasoning and planning-based tasks, which require what we would consider high-level features like inter-object relationship, common sense knowledge, knowledge of physical laws, etc. So, for example, in the image shown here from Zeller et al., a reasoning model needs to have knowledge of how a restaurant works to understand why the person on the right is pointing to the person on the left. So this is a slide I borrowed from Joshua Bengio's talk at AAAI 2020. And he talks about this idea of deep learning 2.0, sort of what are the new representation learning paradigms that will need to be addressed by deep learning for it to evolve beyond the current state. So some of these are like learning features that generalize out of distribution, either out of the box or with few shot training. Next is learning causal features and also learning decision rules that can be explained causally. Next is an agent perspective. So this is sort of the embodied AI that I was talking about before, an agent which learns by interacting with its environment and learning from experience. Next is utilizing high-level semantic representations, such as understanding visual concepts, inter-object relationships. And the last one is learning compositional features of concepts, such that they can be brought together at inference time in multiple ways to reason systematically. So it's been shown that deep learning models are good at learning abstractions from raw data, but when it comes to performing on discriminative learning tasks. However, these abstractions may or may not correspond to knowledge concepts that humans learn and understand, and they suffer from what's called the binding problem. So, which is the inability to dynamically and flexibly bind information that is distributed through a network. So as a result of like the binding problem, these deep neural learning models have a hard time performing iterative reasoning over the abstractions that they learn. So in the example I showed, this is a problem in computer vision called visual question answering, where the model is given an image and a natural language question, and it has to answer the natural language question based on the image. So a simple question which involves discriminative tasks such as what is this, is answered correctly. And even though we can think of the neural network having information about features such as blue and cylinder and color and size distributed throughout the network, when it's asked a complex reasoning question, and this is not probably complex by cognitive science standards, but in computer vision standards, it has a hard time dealing with this. And one cause of this binding problem is that the representations learned by neural networks are often not compositional. For a simple example, consider the case where a model learns abstractions for visual objects and their attributes. We humans tend to have an easier time disentangling the objects and attributes in terms of knowledge concepts. And thus we are able to compose these concepts in various ways to understand and reason about visual domains. However, this is still challenging for neural networks, and there have been several data sets designed to both test this ability in models and also sort of train newer models that have this ability. But in general, like it's been demonstrated that deep learning models suffer from a performance drop-off on a test set consisting of new compositions of objects and attributes. And here is an example of such a data set. Oh, I see something in the chat. Oh, yeah, I guess I shouldn't have said stoplight. So here is an example of one such data set which tests for compositional reasoning in visual question answering. This is called the CLEVER data set, which stands for Compositional Language and Elementary Visual Reasoning. This was work done by researchers at Stanford, I believe. So the data set tests for both the ability to learn useful abstractions from raw visual data, such as attribute types, number of objects, etc. And then reason about these learned abstractions by answering natural language queries, such as on comparisons, logical operations, spatial relationships. Now that I've mentioned like that neural networks are not very good at disentangling individual concepts in the representations that they learn, and this being the reason that they perform poorly on compositional reasoning, I would like to sort of consider the other key paradigm in artificial intelligence, which is symbolic models. And symbolic models in maths and computer science are very good at performing composition of information. So one example would be logical expressions, which compose symbolic representations to generate decision rules. Another example is functions used in programming. Both are shown here. And for example, their applications to systematic reasoning involve rule-based programming. So rule-based programming is the foundation of the symbolic AI-based systems that sort of attempt to emulate stepwise decision-making to solve problems. And inference in symbolic AI passes the information through a sequence of units. Sorry. And these units can be, for example, the logical expressions we saw before. And then it culminates in a conclusion that answers a given query. However, while these are very good at expressing compositions, these tend to suffer from knowledge acquisition problem, which is sort of this inability to leverage unstructured data to derive new computational units and improve existing ones. So for example, in the functional program I showed before, it's not obvious what this function has whiskers for a cat should look like, has retractable claws for a cat should look like. Just To sort of repeat what I discussed before, neural models are good at learning abstractions from large amounts of data and at discriminative performance, which symbolic AI has a hard time with, while symbolic AI is good at efficiently reusing knowledge concepts and performing iterative computation useful for reasoning. Next, we'll consider approaches to infuse neural models with the benefits that come from symbolic reasoning. And this is work done by Jacob Andrews at UC Berkeley. So they sort of broke down reasoning problems as a procedure composed of smaller reasoning problems, which then come together in almost a Lego-like manner to solve this bigger reasoning problem. And while at the test time, the model might encounter a completely novel combination of these blocks, these Lego blocks, it's also likely that these combinations will be made up of smaller blocks that have been seen before. So, for example, in question answering, if we have two different questions, such as what color is this thing with the same size as the blue cylinder, and how many things are the same size as the ball, there's this block on comparing size, which is shared across both these questions. And in order to exploit this compositionality in reasoning problems, the authors considered each underlying reasoning problem as a small pattern recognition task that can be solved by a neural network. So for example, for compare size, we can have one small neural network which takes as input two object path images and compares their size. And furthermore, since the problems share a lot of these reasoning blocks, these small neural modules, the authors call these neural modules, can be shared across problems. And in practice, these networks, which are called neural module networks, are quite computationally efficient as they share parameters across these reasoning problems. And also, in many cases, the modules themselves, so for example, the module to find a ball and the module to find a cylinder, it can be just the same neural network which is capable of object recognition. So this is what a full neural module network sort of looks like. First, the natural language question is parsed through a dependency parser to generate a structured representation of the question. Then corresponding to each node in the dependency parse of the question, a small neural module is placed for that node. And this image, for example, the different blocks represent a neural module corresponding to one node in the dependency parse. And just to note, the parameters can be shared across modules. So for example, the blocks in the same color here, such as fine gold, fine big, fine red, are the same neural module, which has parameters. The parameters are just one set of the neural module. And then the modules themselves can be shared across different image question data points. And in practice, the author showed that a small number of neural modules. So initially, when this paper came out, they had specific modules such as attend, which would take an input image and highlight some portion of the image. And then they had modules like transform or translate, so which would take a attention map on an image and translate it up, down, left, or right. So these are the sort of modules that the authors proposed. So they had about 6 or 7 neural modules that their entire network was made of. But in follow-up work, it was shown that even having as little as 2 to 3 modules was good enough for answering the sorts of questions that come up in the clever data set. So for now, I'll skip over the implementation details of the parser and the modules. One reason being that this often varies across research papers. But in summary, these models are trained end-to-end using gradient descent optimization. The parameters of the parser and the neural modules are learned without added supervision as to what type of function each module should represent. So um, this is useful also because it lets the modules adapt to new functions in the test set, and also because it is much more computationally efficient than having a huge library of functions for the module network. So this was a brief summary of the sort of reasoning problems and one way to uh, combine symbolic and neural AI models for reasoning problems. And next, I'll be talking about the work I did, which is we call this neural structure mapping, which sort of takes this idea of neural module networks and uses it for analogy making in abstract visual reasoning problems. So according to Gentner's structure mapping theory, an analogy consists of a mapping of the relationship structure between a source domain and a target domain, but not a mapping of the attributes. So for example, an analogy between the solar system and a hydrogen atom would involve the mapping between the fact that planets revolve around the sun and an electron revolves around the nucleus. So these are relationships with two predicates, but we do not think of mapping over the attributes. So for example, the sun has attributes like yellow, hot, massive, and while making an analogy between the solar system and an atom, we don't think of the nucleus as being hot or massive. And the task we were looking to solve is that of Raven's progressive matrices. So Raven's progressive matrices are a test of abstract visual reasoning in humans, and it has been shown that performance on these tests is correlated to fluid and general intelligence in humans. And over the last couple of years, these have been popularized in computer vision as procedurally generated data sets with training images, candidate labels, as well as rule labels have become available. Examples of such data sets are the PGM dataset released by Google DeepMind, Raven dataset released by UCLA, and the VPROM dataset released by the Australian Institute of Machine Learning. And the task here is that given a matrix of abstract visual scenes with a panel missing and a given set of candidates for the missing panel, the model needs to pick out the correct candidate that should go in place of the missing panel. And in particular, the challenge here is to reason beyond the surface level semantics, such as the object and the attribute values. And in this data set, the authors call the object and attribute together the visual domain of the problem. And in order to complete the Raven progressive matrix task, it is required to use the relationship structure to make the analogy. And this aligns with how structure mapping theory thinks of us as making analogies. And these data sets in computer vision are often explicitly designed with test sets where the visual domain in the test set is out of distribution, as in like it has not been seen in the training set. So this could include novel visual domains in the test set or novel values of the attributes in test set, novel pair of domains between the first row and the second row. And for such test sets, generalization requires reasoning systematically and compositionally using only a subset of visual domains seen during training. So in this paper by Hill et al. From DeepMind, they hypothesized that introducing a prior on the learning process that requires the learning to correctly identify the relationship will align with how humans learn structure. And this is almost sort of a curriculum learning framework where we are shaping what our model will learn by designing a curriculum for the model. And they did this by introducing two possible sets of candidates. So the first set of candidates, which is shown in the top row, they call the learning by contrasting candidates. So these candidates are both perceptually and semantically plausible for the missing panel. So in this data set, they had 4 possible relationship types: progression, and, or, XOR. So the candidates here are ones that will satisfy each possible type of relationship in the row with the missing panel. And the other possible curriculum is normal training. Here the candidates are merely perceptually plausible, but other than the correct candidate, they don't satisfy this semantic relationship with the second row. And the authors showed that if neural networks are trained with this sort of a curriculum where the candidates embody contrasting relational structures, then the models tend to perform better at making analogies. And they also consider a mixed curriculum training where some examples are from the contrasting curriculum and some examples are from the normal curriculum. And in that case too, there was a significant benefit from mixed training as compared to only normal training. So this was sort of the background of the problem and the theory which we want to use. Next, I'll talk about our model. So in contrast to Hill et al.'s work, we considered that explicitly designing a training regime which maximizes structural learning is really not possible outside of procedurally generated domains. So even though in this situation with Raman's progressive matrices, we can do this, but when it comes to sort of real world images, it's hard to have that sort of a curriculum available. And our idea was, what if we could encode the structural information into our model as a prior instead of selecting candidates that maximize structural learning? So we did this in the form of this 2-stage neural network. The first stage is a visual relationship encoder. So for this, we used a multitask model. So first the visual relationship encoder for our model only looks at the source domain. So the first row of the Raman's progressive matrices problem. So it takes as input the first row of 3 panels, and it generates the object, attribute, and relationship labels from these. So in particular, we used a convolutional neural network followed by a recurrent neural network model, but this does not really rely on the architecture of the neural network. We could have easily substituted some other model which takes as input a sequence of 3 panels or a set of 3 panels here. And our idea here was that we want to first isolate the relationship structure from the source domain, and we'll then only use the relationship information for the second stage. And the second stage, we call it the analogy inference engine. And the analogy inference engine is a neural module network which takes the bottom row of target domain panels, and it also takes all 4 candidate panels. And then it selects the candidate panel, which corresponds to the highest softmax probability for the source relationship. So we already have the source relationship extracted from the encoder. And then using the inference engine, we generate a probability distribution over all possible relationships for all 4 candidates. And then we choose the candidate which has the highest probability source relationship. So we do explicitly use the relationship structure in this way, but that is not the only way we explicitly use the relationship structure. We also use it to set up the layout of this neural module network. So in this diagram here, the blocks are the neural modules, and blocks which have the same color are the same neural module with shared parameters. So the modules here are, so first each panel is processed through a convolutional neural network stem, which is just a few layers, a few convolutional layers that extract the visual features from the panel. And then each module consists of what are called residual blocks. So these are 2 neural network layers, one followed by the other with a skip connection in order to let the neural network simply learn an identity mapping if it wants to. So the modules are residual blocks, and we use only 3 types of modules based on the input arity of this module, so the number of inputs that it can take. We use the unary module, which we show with green, or a binary module, which we show with blue, and the classification module, which is again a binary module, but instead of generating features, it generates probabilities over the 4 possible relationships. We saw how module networks are laid out in the visual question answering problem setup, but in abstract visual analogy problems, there is no rich compositional structure which is available from the natural language based question in the visual question answering problems. So it is not obvious how the modules should be arranged to form our modular neural network for reasoning. And I admit that this is very much an open research problem. For our project, what we did was we sort of utilized the domain knowledge about the problems in Raven's progressive matrices to help generate these layouts. Specifically, since we were dealing with either unary relations like progression or binary relations like AND or XOR, we sort of decided to limit the possible layouts to 2 for each type of relationship. And in Raven's progressive matrices, the problem is set up in such a manner that the relationships can be either unary, binary, or ternary, not more than that. So if it's depending on the number of panels in each row and column. So even if the size of the reasoning problems is increased, the possible layouts for our modular network will not increase by a lot. And at inference time, what happens is the encoder first deduces the relationship from the source domain, and then the layout of the inference engine. So the way in which these panels are routed through the modules, it's selected based on the source relationship. And the modules, which are the actual neural networks with parameters that are learned, these are shared across different instantiations of the neural module network. Next, I'll talk about the results. So the first stage results, so the visual relationship encoder doesn't really have to perform any sort of systematic generalization. It only looks at 1 row of images and generates the relationship label. And we found that this does not suffer from the performance drop that happens in systematic generalization which is somewhat obvious because there is really no systematic generalization that we are testing for here. But essentially what we show here is that we are able to achieve a high degree of accuracy in um, classifying the correct relationship structure from the source domain. And for this, the visual relationship encoder, we used a weighted loss setting. So we weight the importance of classifying the correct relationship twice as much as the importance of classifying the correct object or the correct attribute, because we found that in practice this worked well. Next, I'll talk about the performance on the candidate selection accuracy, which is actually what the analogy problem is concerned with. And I compare it here with some standard end-to-end trained deep neural networks. So here there is two test sets that I consider, either a novel visual domain where the object and attribute combination has not been seen previously in the training set, or the normal attribute values test setting where the training set has a different set of attribute values. So for example, 1 to 5, and the test set has a different set of attribute values 6 to 10. And we showed competitive performance when it comes to candidate selection for analogy making compared to the methods that Hill et al. Had proposed. And this was, we find these results promising because our model is much smaller compared to the models used by Hill et al. So for example, our module networks, each module is just 2 neural network layers. So at max, our modular neural network can have a depth of 12 layers, whereas for example, the ResNet model that I write here, so it consists of 50 neural network layers, 50 convolutional neural network layers. And we also use much fewer feature maps. So feature maps are sort of number of individual features learned by the convolutional neural network parallelly. So we use only 8 feature maps, whereas, for example, the WREN, which is a relation network from the original authors, it uses 32 feature maps. So computationally, we were anywhere between 1/5 to 1/4 compared to these models. But in terms of performance, we did competitively. In several cases, we outperformed their models. And in particular, I would like to highlight the results from the last table, which compare model performance in the absence of a curriculum on the training data. And this is the case with normal training candidates, where there's no contrasting structural differences among candidates. And our model performs better compared to end-to-end trained models in this scenario when tested on novel domains and novel attribute values. And this showed that at introducing a prior on the model that encourages structural learning can make up for the lack of such a prior in the data set, which was very encouraging to see. And lastly, this is like a small sanity check experiment that we ran to determine that, sort of determine the importance of mapping the correct relationship structure on the candidate selection model. So we selectively fed each possible relationship combination to the model. So for example, for the second stage of our neural structure mapping framework, we considered each possible relationship and then compared how it performs compared to each ground truth relationship. And we saw that the candidate selection accuracy is significantly high when the correct relationship structure is fed to the module network versus when it's not. So these are the diagonal entries in our matrix here. So to summarize, we introduced a two-stage neural framework for learning abstract visual analogies, which borrows some of the ideas in structure mapping theory. And we showed that our approach is able to generalize systematically to novel target domains while being very computationally efficient. And it is also able to compensate for the lack of a prior in the training regime that maximizes structure. And we also check that it does successfully exploit the process of extracting and mapping the relationship structure. However, there are still a few open questions that we would like to answer. The first is, if there is a way we can learn the representation encodings without training labels. So in neural model networks, in the visual question answering setting, there have been works which do not rely on like the dependency parse labels, and the way they are trained is using reinforcement learning. But these have been shown to be very computationally inefficient. The training often does not converge, and it's still very much an open problem, how to train without these structured labels. And in the other open question is how to learn the architecture of the module network in the absence of structured language grounding. And one thing that we noticed in our ablations was while there was some benefit from using a dynamic layout, there was not a lot of benefit. And we would like to investigate this. One potential reason we can think of is that the analogy making problem in Raven's progressive matrices is very limited. There's only 4 possible relationships, and there's only 2 possible types of relationships, unary and binary, compared to the set of relationships that we have in visual question answering. So this could be one potential reason for this, but this is something we would like to investigate in the future. And lastly, I'll like to briefly cover this great paper that I came across, Neural Interpreters. This is by Rahman et al. The paper itself is titled Dynamic Inference with Neural Interpreters. And this is along the same directions of research, not specifically for analogy making, but in terms of having a modular neural network composed of functional modules. But then the authors here presented ideas that can learn without structured representation of the input. So this is an overview of the architecture, and I'll not go into great detail about this architecture. There's a lot of bells and whistles that the authors use to make this work, but I'll try to give a big picture overview. So the inputs to a neural interpreter is a set of vector values, and the output is another set of vectors with the same cardinality. So for example, these inputs can be vector embeddings of words, images, etc. And the architecture of the neural interpreter model is based on the transformer neural network architecture. And for example, while training, the class information is passed through to the model through a special vector. So this is standard in transformer neural network architectures. This vector is called a class token. And the output corresponding to this class token is finally passed to a simple linear classifier to generate the class labels. So this is the overall model. And inside the model, the architecture consists of a sequence of layers. The authors call these layers scripts. We can think of the script as in a neural interpreter model as the equivalent of a convolutional layer in a convolutional neural network. More specifically, if we think about the transformer architecture on which this model is based, the script layer corresponds to a multi-head self-attention layer in transformers. And the architecture can potentially be just made of one script layer, but the author showed that a stack of layers tends to perform better. However, this of course comes at the cost of extra computation. So up until this point, a neural interpreter seems akin to a standard feed-forward neural networks with a set of inputs and outputs and a sequence of layers. However, inside each script layer, the neural interpreter performs dynamic inference, similar to neural module networks. And I'll give a high-level overview of how this works without going into the details of the operations. So each script layer consists of 4 types of operations or 4 components. The first components are functions. So the functions here are represented by the colored blocks. So we can think of functions as vector computation units, which are shared in the neural network. And the function can be thought of as an instruction set for other components in the script. Each function consists of 2 vector units, a signature vector and a code vector. And the signature vector tells the type matching component, which we'll talk about later, what inputs should be routed into this function. And the code vector tells the interpreter component, which we'll talk about, how to process the inputs that are coming into this function. The second component is the type inference mechanism. So this whole architecture, it's inspired from typed programming languages. And the idea was, is there a way that we can build typed functions, which are functions that have a defined signature as to what sorts of inputs they can take through neural network parameters and then learn these functions. So the second component is a type inference mechanism. This is a simple feed-forward neural network that takes each input from the set and generates what they call a type vector. And we can think of this as a vector representation of the variable type. So for example, when we define a function in a program, the function takes some inputs and there is a defined type for each input that the function can take. So this is a vector approximation of the equivalent idea from programming. The third component in this script layer is a type matching mechanism, which learns how to dynamically route the information from the set of inputs to each function. So the way it works is it receives the type vector from the input and the signature vector from the function. And it simply generates a binary mask, which decides whether an input element will be processed by a function or not. And the final component is the interpreter mechanism, which we can think of as roughly corresponding to the programmable neural modules in the neural module network. So the interpreter consists of several parallel, linear, and self-attention layers on the input set elements. So these are shown by these blocks, parallel blocks here in the second image from the left. So each of these layers is conditioned on 2 vectors. First is the code vector of the function, which determines how each input will be processed by these layers. And second is the mask generated from type matching, which determines how much of a set element will flow into this function. And thus the interpreter broadcasts each input element into parallel computation streams. And then finally, it performs a weighted aggregation of each stream. And the weights are determined by, so the weights are determined by the type matching vector. So by how much of each input should be, how much of each input is compatible with each function roughly. So this is almost a very core, crude, and rough overview of this model. The key idea here is to build a neural network that kind of corresponds to how we write programs in computers. It operates on a set of inputs. It dynamically routes each set of input to a set of functions, and these functions are learned via end-to-end gradient descent training. Okay, this is the results that they reported. So the neural interpreter paper, it's not specifically tailored for one particular task. It's a very general neural network architecture, but the authors tested it on the PGM dataset in order to evaluate its ability to generalize systematically. And this dataset is very similar to the abstract analogy making dataset that I showed earlier, except there is 3 rows of panels, and the matrix completion task here involves ignoring confounding visual relationships, which might be present in one row but not present in both rows. And in this data set as well, there's no curriculum in the training set. So this corresponds to just normal candidates. And the authors of the neural interpreter paper showed competitive or better performance than relation networks. So these are the WREN and VAE WREN in this table. Graph neural networks, which is MXGNet, and vision transformers. So in this table, particularly the last column, the extrapolation column, it corresponds to our extrapolation setting, but the other columns, these are specific to the data set that these authors used. So to summarize, like, I think this idea of substituting functions in a functional program with neural network layers and then learning both the layout of the program and the role of the functions themselves, it's an interesting way to build the useful ideas from symbolic AI into neural AI. And our results and the work from the authors of neural interpreters shows that these models are good at systematic generalization to novel object and attribute combinations in visual reasoning. And in general, I'm excited about this direction of research. And I think that's the end of my slides. Thank you everyone for joining me. I'd like to acknowledge my advisor, Professor Graham Taylor. And also the presentation format is borrowed from Dr. Eric Taylor, who was also on my advisory committee. And I'll be happy to take any questions now.